It is my pleasure to welcome Jimmy Irwin, who is visiting us from the University of Alabama, where he is a professor. Jimmy obtained his PhD from the University of Virginia, and his main research interest is hot gas around supermassive black holes, X-ray binding populations in galaxies, ultraluminous X-ray sources, intermediate mass black holes, X-ray emissions from hot gas in early type galaxies. Today, he is going to tell us about giant rapid X-ray flares in external galaxies.
Thank you for the introduction. Yes, I'll be talking about recent discovery we've made of two giant flares that occurred within globular clusters of nearby galaxies. But before I get into the talk, I want to discuss, just say a bit about how this project got started. It actually got started when two University of Alabama undergraduates came to me and wanted a project to work on for the academic year. And I knew that given their heavy course load, they wouldn't be able to donate more than a few hours per week on the project. So I wanted to give them a project with a sort of gentle learning curve, something that they didn't have to work too hard on learning in-depth gender analysis. So no abstracting spectra, no fitting with expect. I wanted to give them a rather simple timing project to work on, looking at the timing characteristics of X-ray sources around nearby galaxies. Now, the original idea was not to look for X-ray flares. It was basically to find additional examples of black hole candidates in globular clusters. Now, without going into the long, storied, and sometimes fiery history of whether globular clusters harbor black holes or not, mainly this controversy stems from the fact that we can't find any concrete examples, any confirmed examples of black holes within our own Milky Way globular cluster population, either of the stellar mass variety from the collapse of massive stars or the always contentious intermediate mass black hole variety that might reside at the centers of globular clusters. So the idea has been in recent years to use the globular cluster populations from external galaxies to increase the number of globular clusters for which we had to search for. And the idea is that if there's a black hole there that is accreting at anywhere near its Eddington limit, it should be a strong X-ray source, right? So looking for an X-ray source whose X-ray luminosity exceeds that of the Eddington luminosity of a neutron star, that would be a good candidate. Now, I say as a caveat, we've learned in the last year that not everything that is luminous turns out to be a black hole. The ULX, X2, and M82 turned out to be a neutron star. So we do have to be careful in just sort of blindly assigning black hole status to anything that is 10 to the 39 or 10 to the 40 first per second. But nonetheless, we started this project before this was known. So we went ahead with the assumption that the bright sources we find would be a good place to start looking for black holes. Now, ever since Chandra was launched, it became a thriving industry to match the point sources around galaxies to globular cluster lists. This has been done many times. One of the first ones was by Angelini et al. With the elliptical galaxy NGC 1399. Most of these point sources you see are neutron stars or black holes that are within this particular galaxy. And the white circles show the X-ray sources that are coincident with globular cluster list as determined optically. This has been done many, many times. Many groups have done this. Pepe and Dong Wu's group has done this for a number of deep stares at Chandra has looked at galaxies. And the general consensus is that a high fraction of these X-ray sources are found within globular clusters, sometimes exceeding 50% of the sources are found in globular clusters. So the original plan for the undergraduates were to do a larger search using a larger fraction of the archive to try to find sources that fit two characteristics. One, they need to be at least as luminous as 10 to the 39 Earths per second to be safely above the Eddington limit of a neutron star. And importantly, we wanted them to show significant X-ray variability. This would rule out the possibility of a large number of fainter neutron star binaries that were masquerading as a single 10 to the 39 Earths per second source. At the distance of these galaxies, Chandra could not resolve multiple sources within the same extragalactic globular cluster. So it had to show variability in addition to being luminous. Now, eventually, the first candidate was found in 2007. Macaron et al. Had a Nature paper there that found detailed the finding of a globular cluster that harbored a very luminous X-ray source, shown in the image there, the XMM image within the green circle. Now, at the beginning of the XMM observation, the source was very luminous, several times 10 to the 39 Earths per second, order of magnitude above the Eddington luminosity of a neutron star. But at about the 20,000 second mark, the source declined in luminosity by a factor of 7, clearly indicating that this was emission coming from a single source and not a collection of, for example, neutron star binaries. And this was touted as the first firm example of a black hole within a globular cluster. And several followed in following years. The same group, 3 years later, found a source in NGC 1399, which, for the most part, over most of the 60,000 second observation, wasn't all that spectacular. The integrated luminosity over the entire 60,000 seconds was well below 10 to the 39 ergs per second, and people missed it. I'm embarrassed to say I'm one of the people who missed it previously. I analyzed this same data set years before, didn't notice that it was emitting above 10 to the 39 ergs per second for the first 10,000 seconds. So it was missed until it was published in 2010 by Shi. But it also shows the same characteristics. Above 10 to the 39, strong variability, indicating that it's a single source. Now, combing through the literature, I was able to find 4 other examples of sources which at some point exceeded 10 to the 39 ergs per second and were variable, shown here between 2010 and 2012. They're all rather similar in that they peaked right around the Eddington limit of a 10 solar mass black hole. But the idea for the project was to try to find more of these, right? These were sort of selected galaxies, the best candidates, the biggest galaxies, the most number of point sources. The idea would be for the Alabama undergraduates to go through a larger fraction of the Chandra archive and try to find more of these. Now, when you're dealing with a bright source, in the conventional terms, when you have a source with a lot of X-ray photons, you do the normal thing, you define fixed time bins, and you determine the count rate within that time bin, and you look for strong variability. This is just a random plot that I pulled from the internet. I didn't work on this one, but it shows what a traditional X-ray light curve is going to look like. And a source like this, of course, is highly variable. We don't have the luxury of dealing with a lot of photons when we're looking at X-ray binaries at the distance of Virgo or Fornax, where most of our galaxy samples were located. You might only get 100 or 200 photons during a 40 or 50,000 second observation. You really can't make a traditional light curve with very many bins and extract the maximum amount of time information from that. So we try to go about this in a slightly different way. Instead of doing fixed time bins, we searched for flares of a fixed number of photons. So we're looking for photon bursts rather than having fixed time intervals, right? This is a way for us not only to find variability for low photon sources, but also to find very quick variability that might disappear on short time scales that might be lost within a more traditional time binning technique. Now, to illustrate this a little better, we created cumulative photon arrival time plots. So in this particular example, this is an average source in a galaxy, a 40,000 second Chandra observation. This particular source, there are about 130 photons detected by Chandra, right? So we start with the first photon at time 0, at the beginning of the observation, and the arrival time of each subsequent photon is added to the cumulative total to get a stepwise function all the way up to the last photon detected at the end of the observation. So the idea is to look for photon bursts within the light curve. Now, of course, we didn't do this visually. We had an algorithm that would search for bursts on various photon burst scales. We started with a burst of 4 photons. We compared the arrival time of photon number 1 to photon number 5, compared the count rate within the delta t of the arrival time differences between those 2 photons, compared that to the count rate for the entire observation, and saw whether that was statistically different from the average rate. Then we'd go from 2 to 5, photons 3 to 6, 4 to 7, work our way up the curve till we got to the very end, and then do a statistical analysis as to whether that 4 photon bin burst represented something significant, above and beyond what you would expect from random Poisson fluctuations in the count rate. Then we come back down and we'd start with 5 photon bursts, photons 1 to 6, 1 to 5, 2 to 6, 3 to 7, all the way up. Come back down, bursts of 6, 7, 8, all the way up to 20. So we were looking for photon bursts on a variety of burst scales. Now this particular source shows a little bit of wiggles back and forth, but by and large it's consistent with a flat rate. Those little wiggles can be fully explained by small random Poisson fluctuations in the count rate. So this is an uninteresting source. And this represented, of course, the vast majority of sources that we looked at. I told the undergraduates, if you do find an interesting source, first look for an optical counterpart in SIMBAD. this method is actually pretty good at finding flaring M-dwarf stars, which are interesting, but they were not the point of our project, so we set them aside. So if they found in Sinbad an optical counterpart that was 13th or 14th magnitude, that's much too bright to be a globular cluster at that distance. So they set those aside, and they only came to me when they found something that was, did not have an obvious optical counterpart, at least in a database like Sinbad. Now, it was the probability that you could get a burst of that number of photons over that amount of time compared to the total rate. So if you expected 1 photon every 500 seconds and you got, within that time frame you expected, say 0.1 photons and you got 5, you could work through the numbers to determine how many times that would happen randomly from a Poisson fluctuation. And if it was above a certain threshold, we started out at 1 in 100,000, then we looked at that for further analysis. If it was below that, we assumed that it could be a random fluctuation. So we're really only looking for the ones that showed very, very strong probability of not being a random fluctuation in the count rate.
You took into account the number of independent things?
Yes, we corrected for the look elsewhere effect, how many independent 4-photon bins we would have had in each source. We did correct for that. That's why we set our threshold so high, so that we didn't run into problems like that. Anything we found was way above what any reasonable person would assume to be variability. I'm not going to display anything that shows kind of borderline significance in terms of the flares. So eventually, one of the undergraduates came to me, and they found a very interesting cumulative photon arrival time plot. This particular source rose rather quickly for the first 10,000 seconds of the observation, and then kind of flattened out and emitted at a more meager rate, more subdued rate for the rest of the observation. We were excited for about half an hour until we looked at the coordinates, and we realized this has already been discussed. Actually, this was the source of NGC 1399 that I showed a couple plots ago. We found it independently well after the fact, but it did go to show us that our method was working in finding the sources that it should have detected. These are the kind of sources that we were hoping to find. We just happened to find one that was already known several years previous. They came to me with another one that looked really bizarre. You see right here, the plot goes nearly vertical at one point. Vertical means that you're getting a large number of photons in a very small period of time. You're excited for a little bit on this one also. It turns out Peter Jonker had published this back in 2013. Really don't know what this is. It has a very faint and apparently transient optical counterpart. So really don't know what the distance of this is. We therefore don't know the luminosity of this source. It's exotic no matter what it is, but we can't necessarily say that it's at the distance of M86. One, because we have no optical counterpart. Two, because it's quite far separated from the center of the galaxy. It could be a foreground star. It could be a background AGN. At this point, don't really know what it is. Again, our method found this as it should have, but it already had been detected by another group the previous year. Eventually, they came to me with another source that turned out to be rather interesting. It was in the Virgo elliptical galaxy NGC 4636. Now, rather than give its long Chandra name from now on, I'm just going to call it source 1. Okay, so the source 1 is going to be the NGC 4636 source. Now, this particular source wasn't all that spectacular when viewed from the viewpoint of the entire observation. Over the 75,000 second Chandra observation, about 160 photons were detected, about 1 photon every 500 seconds. So keep that number in mind for future reference. Given the spectral model we assumed by fitting the source, that corresponds to 6 times 10 to the 38 ergs per second. Yes?
What was the background level compared to the source level?
Very small, maybe 1 or 2 photons total within the PSF extraction. So we didn't have to worry about background for Chandra. XMM, that's an issue. For Chandra, we didn't have to worry about background. Right.
What spectral model did you assume?
We fit, with the meager number of photons, we fit just a simple power law, and it was about 1.6. The slope was 1.6. So typical of extragalactic X-ray binaries. Nothing, not particularly hard, not particularly soft, based on studies of other X-ray binaries in other galaxies. So this doesn't reach our threshold of 10 to the 39 ergs per second overall, right? If you look at any large galaxy with Chandra, you're going to find a handful of sources that are this luminous or more luminous. So that alone isn't all that spectacular. This is why this source didn't receive any attention in the past. But you'll notice probably by eye, that about 11,000 seconds into the observation, something happened. Okay, the plot went nearly vertical during that time. It was chugging along at several times 10 to the 38 ergs per second, and then all of a sudden the source turned on, and then gradually faded, and then became constant again, as if nothing had happened. Right? Now we can zoom in on this region of time right around 11,000 seconds, and we can see that the source was emitting about once every 500 seconds, and then all of a sudden, at one point, you get 6 photons in 22 seconds, about 1 photon every 4 seconds, compared to 1 photon every 500 seconds for the global average. About a factor of 100 increase in the count rate during that time. After those first 6 photons came in, the source began to fade somewhat. It was still elevated, but eventually faded back down. But during that 22-second time period, those 6 photons represented a luminosity that was approaching 10 to the 41 ergs per second. A huge increase over what the source was doing before and what the source was doing immediately after the flare ended. Now, breaking down this flare into subintervals, if we look prior to the flare, the first 29 counts came within 11 kiloseconds. Again, the rate that I quoted earlier, approaching 10 to the 39, but not quite 10 to the 39 ergs per second. Those first 6 photons came in 22 seconds, a very high luminosity. The first 12, so this is cumulative, first 12 came in about 3 minutes. It still maintained luminosity above 10 to the 40. The first 18 came in about 10 minutes. And then finally, the flare ended after 24 photons was emitted, after about 22 or 23 minutes. Still maintained an average luminosity over the entire flare of several times 10 to the 39 ergs per second. And then it ended. Okay, the next 6 photons came in at actually a somewhat lower rate than the global average, only 3 times 10 to the 38. And then it continued out kind of where it was before. Okay? Whatever this flare was, it does not seem to have affected the overall accretion mechanism of this particular source. It was there for 20 minutes, and then it disappeared. If you had blinked for 20 minutes, you would not have found this source. And indeed, we've looked at other Chandra and XMM epochs of this source, and it looks just like it does in the non-flare state. It's the only flare that we detected. Now, these luminosities, of course, assume that the source is actually at the distance of that galaxy. And it turns out there is an optical counterpart to this source. Now, this was actually noted back in 2009 in a paper by Photon Brown, who matched up the X-ray positions to the globular cluster positions as determined by ground-based optical photometry of Dersch et al. In 2005. Now, this was photometry, so these were not spectroscopically confirmed globular clusters, but they were globular cluster candidates. And the particular source that we're interested in had a approximate R-band magnitude of about 23, rather faint, but it had a Washington photometry C minus T1 value that was fully consistent with being a globular cluster. Now, as Photon Brown noted in their paper, follow-up work by Schubert et al. Took a subsample of these candidates by Dersch with the colors that were indicative of a globular cluster, and found that a very high fraction of them turned out to be globular clusters when they were when spectra were taken of them. So they are truly bona fide globular clusters. This one, unfortunately, was not in their sample. But I do point out that in looking through Schubert's paper, if you focus on field 1, which is where source 1 is located in, within this box, for which they did contain, Schubert et al. Did obtain spectra, for those which were in a half magnitude range in color between our source of interest, between 1.44 and 2.44, there were 54 sources that they got spectra from. All but 2 turned out to be globular clusters, and those 2 were foreground Milky Way stars. So at the 96% confidence level, we can be pretty sure that our source is a globular cluster based on its colors. Of course, that's not 100% proof. We do want to go back and get optical spectroscopy on this particular source to verify it's at that distance, but we are fairly confident that this will turn out to be a globular cluster at the distance of NGC 4636, if indeed we're able to get a spectrum of that particular source. Now, our confidence in this being a bona fide globular cluster was bolstered by the fact that a little bit later, the undergraduates came back with a second example that, as I'll show briefly, really is at the distance that we think it is. It really isn't a globular cluster of the host galaxy. This one occurred in NGC 5128, or CEN-8, much closer to us than the Virgo, only 4 megaparsecs away. Now, from now on, I'll call this source 2, just for ease. Right? And you can probably see, just from the image, that there was quite a significant flare that went on in this source also. Prior to the flare and after, you're getting about 1 photon every 1,000 seconds for a very modest luminosity of 2 times 10 to the 37 ergs per second. These kind of sources are literally a dime a dozen in nearby galaxies. It would not draw any attention to itself at all based on a luminosity of only 2 times 10 to the 37. But just like the 4.6, or just like source 1, source 2 turned on almost immediately. 10 photons coming in within a 51-second time frame, one count every 5 seconds. This is about a factor of 250 increase in the count rate when this flare began. It also began to tail off on time scales of 15 minutes or so, 757 seconds. It maintained a pretty high luminosity over that threshold. Again, close to 10 to the 39 Earths per second. And then when the flare was over, it goes right back to what it was doing, chugging along at a few times 10 to the 37 Earths per second, just as if nothing had happened during this time frame. Now, fortunately, Sen-A was observed many times. It was the target of a very large project by Chandra. There's many epochs of Sen-A. There's over 30 Chandra epochs of this particular galaxy. So this was taken on March 30th, 2007. 18 days later, it flared again. In another observation, right around the center of the observation, it was chugging along at its nominal rate of a few times 10 to the 37, and then 6 photons came in within 22 seconds, about 1 every 4 seconds, approaching 10 to the 40 Earths per second. It also lasted on the order of 12 minutes or so.
What ACES mode are you using? Is it the 3-second integration?
It was a 3-second integration.
So you're very piled up. The 6 photons are 20%.
We could be.
6 and 7 readouts.
They were off-center, so the PSF was larger, so that mitigated it somewhat. But you're right, we could be somewhat affected by pile-up, but it shouldn't be too significant. At least we don't think it's going to be too significant, given the somewhat larger extraction region we had to use. And the same thing for 4636. It was nearly 3 arc minutes off-center from the aim point. So again, it would spread the photons out a little more than we would if it were on axis.
It's still 6 and 7 or 8 readouts, and that's the most you can have.
Yeah. Yeah, so it's probably close to being piled up. So you could view this as a lower limit.
So it's even higher.
It could be even higher flux, yes. Yes. Yeah, okay, yes, it is higher flux. I won't argue with you on that. So this was source number 2. Sorry, it was epoch number 2. It was observed again about 6 weeks later, or at least it flared again 6 weeks later, in end of May of 2007. Again, chugging along happily, and then 8 photons coming in 26 seconds. This time it actually did touch 10 to the 40 Earths per second, not even correcting for any kind of pileup at that point. And then when it was over, it goes back to what it was doing. Right? And then once again, a year and a half later, in January 2009, this was a very short observation. It was only a 4 or 5 kilosecond observation. Right at the very end, we got lucky, and 5 photons came in within 35 seconds for a 4th example of a flare in this particular object. So clearly, we can rule out anything strange instrumental features like a cosmic ray afterglow or anything of that nature. It appeared different parts of the detector at 4 different times within Chandra. So it really does belong to that particular to that X-ray source. Now, more recently, XMM looked at this source, and data became public in early 2015, and lo and behold, we found a flare in the same source in the XMM data. Now, XMM is a little bit more difficult because within the much larger PSF, you're getting a lot of background within there. In fact, a lot of this structure you see isn't real. A lot of these photons are background photons that fell within the PSF. But still, towards the end of the observation, you can see this near vertical movement in the Univ arrival photon plot, indicating that there was a strong flare there. You can actually see this visually if you filter the image properly. This is MOS1 plus MOS2, for example, and this is the MOS1 plus MOS2 image for the entire observation. Now, if you squint and turn your head a bit, you might convince yourself that there's a source there. Indeed, it's about 3 sigma significance of finding a source at the expected location in the entire duration of that observation. Much, much fainter than these 2 comparison sources next to it. But once you know where the flare is, and you can filter the image based on that 300-second frame where most of the photons came in, now you see your source very, very clearly compared to the 2 companion sources. During this 300-second frame, it was the brightest thing on the field of view other than the AGN at the center. So hard to see in an entire external observation, but once you know the time frame of when it happened, you can easily see it in the image. Now, by the numbers, at its peak, it emitted 5 photons in 5 seconds, divided among the MOS 1 and MOS 2 detectors. And that, again, is exceeding 10 to the 40 ergs per second. And over the entire time frame of the flare, it still averaged nearly 10 to the 39 ergs per second before it began to fade away right at the end of the observation and go back to its nominal few times 10 to the 37 ergs per second normal behavior. Now, unlike source 1, for which we think it's in a globular cluster, but we're not guaranteed yet, it's a high probability, we know for a fact that this is contained within a globular cluster of Cen-A. In fact, this source has been observed so many times optically that it has not one but 2 different names that people have given it. Right? It's a very luminous object. You see at various wavelengths here. Perhaps the most interesting one is the Hubble Space Telescope image of the source. Not only is it extended, but you can tell that it's actually elongated in one direction. It looks very similar to Omega Cyn within our own Milky Way. It's a very massive, absolute magnitude brighter than -10. Spectra from other groups, from Taylor et al., shows a velocity dispersion of about 20 to 25 kilometers per second, and their mass models indicate a very massive globular cluster. This is more massive than Cen-A and almost as massive as the M31 globular G1. Right? Now, in the literature, there's a debate as to whether these very luminous globular clusters are actually globular clusters, or could they be the stripped core of dwarf galaxies, these so-called ultra-compact dwarf galaxies. It's not exactly clear. It hasn't been resolved yet as to what exactly is this. Was this once a dwarf galaxy whose outer regions were stripped away by interaction with Cen-A, or is this simply a very, very large globular cluster? That remains to be debated. If indeed it is an ultra-compact dwarf galaxy, this raises an interesting scenario. What if this dwarf galaxy had an intermediate mass black hole at the center, 10 to the 4 or 10 to the 5 solar masses? Could that be leading to the flares that we see, at least in this one particular source? And I'll get back to that point a little bit later in the talk. Now, I do want to mention another potential third source that we found by looking through the literature. This was a source in the elliptical galaxy NGC 4697, a work that Sivakov et al. Did back in 2005. Now, the significance of their flares aren't nearly as great as ours. Numerically, our flares, the peak of the flare, you would expect to happen from random Poisson fluctuations about 1 in every 10 to the 12 times. Right? So the odds are less than 1 in 10 to the 12 that those were a random Poisson fluctuation. These flares are more like 1 in 10,000. Okay, so it's conceivable that these flares aren't real. You're getting, in 2 different epochs, you're getting 4 photons in about a minute. That corresponds to around 5 times 10 to the 39 to 10 to the 40 ergs per second. Unfortunately, the Sivakov source does not have an optical counterpart, so we don't really know its distance. Is it a foreground star? Is it a background AGN? Sivakov argues that it does belong to the host galaxy based on its proximity to the center of the galaxy and the fact that you don't typically find AGN with that extreme X-ray to optical luminosity ratio. So they argue that this is indeed a flare in 4697, but it's not exactly clear and may never well be if we never find an optical counterpart to that. But it's potentially a third example of a flare, albeit a somewhat subdued flare that doesn't show the much longer 10 to 20 minute decay rate as we saw for source 1 and source 2. Now we can calculate the recurrence rate and the duty cycles of these sources. For source 1, we're sort of limited by the fact that we only detected 1 flare. So roughly speaking, in the 386 kiloseconds total for which Chandra and XMM viewed this source, it flared 1 time, right, for about 20 minutes. So that corresponds to about once every 4 days, roughly speaking, with a duty cycle of about 0.3%. We can do a lot better with source 2, for which there were 5 flares, over about 1 megasecond total of time between Chandra and XMM. That leads to a recurrence rate about once every 2.2 days, and again, a duty cycle of around 0.3%. So they're really off for a vast majority of the time. If you blink at the wrong time, you're going to miss these flares. And indeed, if Cen-A had not been observed so many times for other reasons, we might not have observed any of these flares. You just got lucky in any one observation that you're going to have a flare going off with this very low duty cycle. So what exactly are these sources? And the honest answer is we don't really know yet. Okay, we have some ideas, and I'll discuss what we think they could be and what maybe they can't be. But just to step back for a minute and look at this in context. If we think about sources in the universe that we know of that are very energetic, by here I'm defining energetic as being more luminous than the Eddington luminosity of a 10 solar mass black hole. For objects more luminous than that, there's a very short list of objects which vary by factors of more than 100 on timescales of less than 1 minute. Now, by going through the literature, I've only been able to find a small handful of objects that do this, and even a smaller number of objects that do this without completely destroying themselves in the process, right? Obviously, gamma ray bursts and X-ray flashes, which are thought to be associated with the shock breakout following the collapse of a star during a supernova event, those are one-time events. We've never seen a gamma ray burst or an X-ray flash repeat itself. So they satisfy this criteria, but of course they destroy themselves. So they cannot be what we see, because our objects don't destroy themselves. They indeed repeat themselves, at least for the case of source 2. It could potentially be what's called a type 2 neutron star burst, for which we see for a couple of sources in the Milky Way. I'll talk about this a little bit more later, but while they do reach 10 to the 40 ergs per second on rare occasions during the burst, the variability just before the most extreme burst really is only a factor of 10 to 20 based on literature searches, not a factor of 100. So it doesn't quite meet this criteria of flaring by a factor of 100 on timescales of less than 1 minute. The only source that type of source that seems to sort of match this in terms of its timing behavior are soft gamma repeaters and their cousins, the anomalous X-ray pulsars. I'll talk more about them a little bit later. They flare up to this luminosity on very short timescales, and they repeat this, so they do not destroy themselves in the process. So, could they be SGRs or AXPs? Now, just briefly describing what they are believed to be, the ones studied in our galaxy, they're believed to be neutron stars that have very, very strong magnetic fields, magnetars, with magnetic fields on the order of 10 to the 15 Gauss. And if their magnetic field lines get twisted enough, they break, and you release a tremendous amount of energy on very small timescales as those magnetic field lines are broken apart. Now, majority of the flares are in the right range, 10 to the 40 to 10 to the 42 ergs per second, and they flare on very small timescales. The most giant SGR flares can exceed 10 to the 45 ergs per second. Extremely rare, but they have been observed on a few occasions that soft gamma repeaters have gone that high. Now, could our sources be SGRs or AXPs? We think not, for the following three reasons. Right? First of all, for those SGRs and AXPs which have luminosities in the range of which we're observing, the flares are very, very short. They're on the order of a second or less, and then they're gone. So they really don't match the same type of rise time of a half minute to a minute and then a decay time on the order of 10 to 20 minutes. That's not what we observe at all. The only SGRs that show longer rise and decay times are the huge flares above 10 to the 45 ergs per second, and that's not what we see here, right? So we don't think that these source 1 and source 2 can be described by the more common lower luminosity flares of an SGR or an AXP. Secondly, when soft gamma repeaters and AXPs are not flaring, they're much lower luminosity than what we see for our source. Our sources have been constant, at least since Chandra was launched for the last 10 years. Even when they're not flaring, they're 10 to the 37 or 10 to the 38 ergs per second during those times. When these types of objects aren't flaring, much, much lower luminosity. Another phenomenological comparison that fails when comparing these SGRs to the sources that we've found. Now, from a more physical point of view, because the magnetic fields are so great, it's assumed that these SGRs or AXPs are very, very young. Right? In fact, they're believed to only exist in this state for maybe a few tens of thousands of years. So you might only expect to find SGRs and AXPs in young populations. Right? Source 1 and source 2 are in very old globular clusters surrounding very old elliptical galaxies. Right? So from a physical point of view, how would you get such a very young, high magnetic field neutron star in a very, very old stellar population? So both from a phenomenological point of view and also a physical point of view, the characteristics really don't match up very well between soft gamma repeaters and source 1 and source 2 that I've described here. I said I'd get back to the type 2 burst on neutron stars. This is believed to be spasmodic accretion onto a neutron star. There's actually only two examples that we know of in the Milky Way. There's the bursting pulsar and there's the rapid burster. And only the bursting pulsar reaches luminosities of 10 to the 40 ergs per second. Now, as I said previously, the variability is more like a factor of 10 to 20 rather than 100 to 500. But could our sources be sort of scaled up versions of this? Again, the timing characteristics kind of break down when we look at it more carefully. The bursting pulsar actually burst for its third time within the past year. It was observed with Chandra as well as other instruments. The Chandra observation showed that in just a 3-hour period, the source burst 7 times. Okay? Our source doesn't do that at all. Our source bursts maybe once every few days. Each burst only lasts maybe a second. So the total energy fluence of each burst is well below the energy fluence of one of our bursts. So again, phenomenologically, it doesn't look like we can explain our sources in terms of type 2 bursts on a neutron star. Furthermore, when type 2 bursts are not outbursting, they have extremely quiet X-ray luminosities, orders of magnitude below the non-flaring luminosities of source 1 and source 2 that we've showed. So at the moment, we don't have any clear analog in the Milky Way to what these sources could be. So we're left to speculate exactly what they may be. All right? Number one, could these be intermediate mass black holes? Everyone wants to find intermediate mass black holes. Are they? Well, it's unclear. Now, one caveat, if the source in NGC 4697, the Sivakov source, which was not located in the globular cluster, if that's the same sort of phenomena, this may not be so good for the intermediate mass black hole scenario. How would you get an intermediate mass black hole out into the field? People have tried very hard to explain ULXs in terms of intermediate mass black holes. If you're going to find an intermediate mass black hole, it makes much more sense to find it in the globular cluster than to find it free-floating out within a galaxy. But, of course, one never knows if this 4697 source is even at that distance, since there's no distance estimate to that source. This IMBH explanation is particularly intriguing for source 2, the one whose optical counterpart could be an ultra-compact dwarf. If so, and if it has a black hole, as you might expect from scaling relations from more massive galaxies, it might have a central black hole on the order of 10 to the 4 to 10 to the 5 solar masses. In that case, these flares need not even be Eddington. They could be sub-Eddington without violating the Eddington limit of a black hole of this mass. Now, this might be more difficult to describe source 1 in this term because the optical counterpart of source 1 is a rather average globular cluster. There's really no evidence that that would be the strict core of a galaxy, of a dwarf galaxy itself. So we're not really clear on that point. Number two, could we have some sort of micro-blazar situation where a beam of radiation crosses our line of sight every 2 to 4 days, leading to an apparent increase of a factor of 100 to 500 in the total flux, the luminosity coming from the source during that period? Possibly. I mean, it's not something that we've seen necessarily in our own galaxy. One particular problem with this is for most of the flares, the profile is a fast rise and exponential decay. It's not clear whether you could get this from a beam scenario where you might expect a more symmetric rise and fall time as the beam crosses your line of sight. Okay, so that's one drawback in any kind of sort of beaming scenario is how do you get these very asymmetric rise and fall times that we see for the source 1 and source 2 light curves. And then finally, could there be something exotic that we haven't thought of before? Could they be so rare that we don't see them in the limited X-ray binary population of the Milky Way? Could there be a way for neutron stars or black holes to exceed their Eddington limits by factors of a lot for very short periods of time by some sort of exotic accretion mechanism that has not been fully appreciated yet? Again, it's pretty much an open book as to what these sources are. We think we know what they're not, but we really don't know what these sources are yet. So any input would be appreciated.
Something that could be totally wrong. But I remember a long time ago when I was studying dwarf novae, SSC, some kind of variability, which is not like this, but the simplest explanation of what we were seeing was nuclear burning at the surface of the neutron star. Mm-hmm. So a situation where you accumulate stuff at a certain quantity. Would that work for a neutron star? Of course, it wouldn't work for a black hole because there is no surface. But if you have a situation in which you somehow you accumulate, you accrete enough where you get critical and then you have a burst and then you decay because that might give you the shape.
Exactly. The type 1 bursts in galactic neutron stars do show the fast rise exponential decay. But in our galaxy, they've all been Eddington limited at the neutron star. If you could find a way to defeat the Eddington limit by a factor of 100, you're right. They have very similar shapes
as
that.
Phenomenon, so I mean,
yeah.
the Eddington limit might not, if it's only a spot anyway.
Yeah, and then I think it would fall into this category. It'd be some sort of exotic mechanism that we don't see in our limited neutron star population of our galaxy. We only found 2 sources within about over 40 galaxies we've looked at. So whatever they are rare. So you're right. It could be some strange analog to a more normal type 1 burst that we see in neutron stars. Okay, so to summarize, I provide some evidence that we're seeing these very spectacular flares in 2 extragalactic globular cluster systems. Something I didn't explicitly say earlier was that, as far as I can tell from literature searches, these 2 events are the most energetic events ever to be recorded in a globular cluster by about an order of magnitude. Right? So they're also spectacular in terms of their location. We just don't see energetic events happening in globular clusters all that often. Certainly not something that touches or comes close to 10 to the 41 first per second. Right? Very similar behavior between the 2 sources. We see rise times on the order of a minute or less, last a few tens of minutes, and they increase in flux at their peak by about a factor of 100 to 500. We also ruled out what we don't think they could be. They don't show very many similarities to these other types of galactic sources that share the common characteristic of reaching 10 to the 40 Earths per second. But as I said, this is a pretty open book as what they could be. Can they be scaled up phenomena of type 1 bursting neutron stars, where you get 100 times more luminosity out during some sort of nuclear burning phenomena happening on their surface? We don't know. I'd like to just end with a comment. Source 1 was taken with Chandra back in 2003, and the Jonker source that I showed at the beginning of the talk, that Chandra observation was taken in 2000. In both instances, these flares sat in the archive for a decade before they were found. Okay? I think this illustrates how, when we think of very short-term flaring, it's mostly confined to the Milky Way, when the studies that are done. But I think there's a growing number of studies now that show that there's a lot of interesting stuff happening on timescales of a minute or less in other galaxies.
Well, Doug, take notes. Maybe we can add something in our catalog for these things.
And we may even want to take this into account for future designs of X-ray missions. Do we want to have frame time readouts that are shorter to account for the fact that when we're looking at extragalactic objects, there may be very interesting timing characteristics happening in those sources on timescales that are smaller than the standard 3-second readout frame that we have now for Chandra. So something to think about in the future. So I think I'll end my talk. That goes without saying, yes. We all want Chandra resolution. Okay. Okay. High spatial resolution, high timing resolution. That's the Christmas list for the next mission. Based on the very limited number of photons we get, like 20 photons, there's no evidence of that. We stacked the SEN-A, and there's no huge difference between pre-flare, post-flare, and during flare. Nothing that we can tell with our statistics. So it doesn't get hugely soft or hard that we can tell based on the few number of photons that we get.
Possibilities. A few months ago, we put out a paper. Jack Steiner was on it, James Biachon, and Bob Fisher, and we called it death by dynamics. And it leads to short flares in the X-ray and also in the optical. And it's a kind of a strange explanation, but it should happen fairly frequently in very dense environments like globular clusters, where you have asteroid strikes on a compact object. Laugh if you want. But actually, so you might think, we don't know in a globular cluster what the population of asteroids is. However, we do know that asteroids are disrupted by white dwarfs, and that the rate that people infer from observations of polluted white dwarfs and from disks around white dwarfs is something like once every 10 to the 5 years, something in the range of 10 to the 18 to 10 to the 21 grams. And that's been studied by many people. So a necessary consequence of that is that in a certain fraction of the time, about 1% of the time, there will be a collision where the asteroid hits. And that could happen after a disruption. You could have a sequence of collisions. So it sounds crazy, I agree, but actually some of this must happen, and the asteroids would presumably be drawn from a mass distribution somewhat similar to the mass distribution in our own solar system. And what happens now, James Guillochon did a few simulations. There's a lot more of this parameter space to be studied, but it does lead to an X-ray flare and also an optical flare when the target is a white dwarf. And you would expect similarly a short duration high energy component followed by a decay for a neutron star as well. So I'm not saying that this is what your flares are, but I think it's something that does lead to flares. I think that's inevitable. And your point at the end about looking through the archives for flare-like behavior would certainly help with these, as would the suggestions about what characteristics you'd like in future X-ray detectors.
I want to comment on Roseanne's remark. I just want to say that was the model people had for gamma reverse before we knew it.
That's right. There's a whole literature on that, and it's a kind of an open question why that isn't what gamma ray bursts appear to be. But it's a very interesting topic, and I know it's changed a lot of the way that I look at this type of phenomenon. Thank you, Paul.
You made Martin very happy, that's why people were laughing. He was going like that.
Oh, okay, I couldn't see that.
Jimmy, if we take your duty cycle and rough recurrence rates that you were saying about once every 4 days, you've looked at, I don't know how many sources in your galaxies. Can you scale that to give, a rough fraction? I mean, it's going to have huge error bars, But, you were saying you don't know how often this happens, but you could start making some sort of, idea of how often this is.
How often you expect to detect one?
Yeah. I mean, given that you've got lots of non-detections.
We have tons of non-detections.
Yeah.
Each observation, 100 sources, multiple epochs, multiple galaxies. We looked at literally thousands, like tens of thousands of sources altogether, and we found 2. It's a very rare event, but when it does happen, it's happened 5 times for one source. So whatever it is, it's repetitive once it happens.
No, I was just wondering whether you could get some rough handle on, what an expected rate is or something.
I haven't worked it through other than to say it would be epsilon.
How far out are you actually able to see this kind of things?
How far would you be able to see them?
Right. And so your rate calculations, I suppose, will be affected by that.
It is. So the one in Sen A, if you put it out at Virgo, you probably wouldn't have seen it. You wouldn't have gotten enough photons to see it. So we're probably limited to Virgo or closer, even for the strongest flare of source 1. The Civicol 4697 source was probably about the same strength as the Sen A source, source 2. And yet you only got 4 photons, and then the flare was over. You move that a little bit further away, you're not going to get enough photons to find any statistically significant flare. So yeah, you're right, we are limited in our volume of probably about 15 megaparsecs with Chandra. Maybe we can go out farther with XMM. But yeah, just due to count rates, we're not going to be able to go out much beyond maybe 4x.
And could these be tidal capture events?
4 to 5 times for the same source? I don't know.
You have something.
I don't know. I have no info on that.
Other questions? Yes.
Yeah, there are some galactic binaries that produce jets at times. So the question is, how much do you have to change the time scale through relativistic effects to get something that's not quite so spectacular?
Oh, so basically you're talking about producing during a...
Yeah.
I have not worked with the numbers on that. The spectrum stays the same, so it's not clear whether you're also boosting photon energies during the event either. So that might dampen the amount of jump, but I don't think it's enough to totally get rid of these flares.
Any more questions, ideas? If not the case, let's thank Jimmy again.